for today's webinar. Today, we are presenting Topological Data Analysis webinar to be delivered by Dr. Vijay Natarajan, sir. A hearty welcome to our respected principal, Dr. C. Nanjundaswamy, sir, for this webinar in his absence. A warm welcome to Dr. Sidraju, sir, our beloved Dean Academics and Professor and Head of Department of Computer Science and Engineering, who is always supportive and the driving force for this webinar. I would like to take this opportunity to express a hearty welcome on my behalf and on our institute's behalf to Honorable Dr. Vijay Natarajan, Mindtree Chair Professor in the Department of Computer Science and Automation, Indian Institute of Science, for honoring our invitation to be today's speaker. I would like to welcome all the participants for this webinar. I now request our beloved Dr. Sidraju, sir, Dean Academics and Professor and Head of the Department of Computer Science and Engineering, to address the participants of today's webinar and to give his valuable inputs.
Thank you, madam. Thank you, Veena. Good morning, all. So I myself, Dr. Sidraju, Dean Academic and the Professor and Head of the Department of Computer Science and Engineering, Dr. Ambedkar Institute of Technology. Today is a very special day for us, and we are going to conduct a regular webinars in various advanced topics. I'm happy to introduce today's resource person, Mr. or Dr. Vijay Natarajan. Sir, first and foremost, it's my privilege and honor to welcome you on behalf of Dr. AIT family and as well as Dr. C Computer Science Engineering Department. My hearty welcome you, sir, for this today's webinar. And I am very proud to introduce Dr. Vijay Natarajan with a small biodata. Dr. Vijay Natarajan is the Mindtree Chair Professor in the Department of Computer Science and Automations at Indian Institute of Science, Bangalore. He received his PhD in Computer Science from Duke University and hold the BE degree in Computer Science and MSc degree in Mathematics from the BITS Pilani. His area of research interests include scientific visualizations, computational geometry, and computational topology. In the current scenario, he is developing topological methods for time-varying and multi-field data visualizations and studying applications in biology, material science, and climate sciences. Sir, really, we are blessed to have today's resource persons to deliver talk on topological data analysis. Once again, I welcome you, sir, for today's webinar. And also, it's my duty to congratulate all my coordinator who have taken a lot of interest to organize this advanced topic, topological data analysis, especially Dr. Gowrishankar, Professor Suresh, Professor Srinivasa, Professor Praveena, and Professor Lavanya, Santhosh, and Professor Veena. Thank you very much, madam, for your interest, and I am looking forward the same in future also. And also, I'm welcoming all my distinguished faculties from the various institutions inside and outside the colleges, and those who are going to involve actively and participated actively. I'm welcoming you all for today's webinar. Have a nice day. Enjoy your days. Good luck, one and all. Thank you very much. Over to Veena.
Thank you, sir. Taking our day further, I'll hand over the session to Dr. Vijay Natarajan, sir. Over to you, sir. Thank you.
Thank you. Let me start by sharing my screen. Okay, hopefully you can see my screen. Thank you very much, Professor Sidraju, for that kind introduction. And thanks very much, Professor Gowrishankar, for organizing this event and and all the others from your team, from the department, for organizing, and for all the participants. Hopefully all of you have something that you can take away from this talk. So the topic of my presentation today is topological data analysis. Right. So my intent with this talk is to give you a broad introduction to this area, with glimpses of results from our group, and then with the relevant background. And all further resources, I'm sure you'll be able to get it from our lab's webpage or department's webpage. Right? So let me get started by talking about our institute. Right? So I come from the Indian Institute of Science. Some of you may have heard of it. For those who don't know, this is one of the oldest universities in the country. We have a very interesting blend of scientists, physicists, chemists, biologists, and engineers who are interested in science problems, coming together to solve some really challenging problems that we are faced with today. Of course, the IISc is known for its research output, but it's also known well for its serene and very nice campus. So hopefully when the pandemic is down and you are able to move freely, you will get the chance to come and visit our campus sometime. I am from the Computer Science and Automation Department. This is a very young department with a lot of bright minds, talented young students, researchers that you will see in these pictures. Very diverse set of students, as you can see. So we have a very interesting PhD and a master's program. We attract some of the best talent in the world who go on to become the future technology leaders, entrepreneurs, and also leaders in academia. Within IISc, I lead a team of researchers within the visualization and graphics lab. So within this lab, we conduct research in the broad area of data visualization and geometry processing. So we have very interesting projects, such as what you can see here. What you can see here on the right is a visualization from biology, where we are interested in visualizing channels in biomolecules. This is in collaboration with a biochemist who wants to understand these protein molecules, these biomolecules, towards drug design. We work with cosmologists, astronomers, who are interested in the study of the universe and its large-scale structure. So we help them analyze their data to uncover the filament-like structures in the universe. In another project, we are interested in visualizing time-varying phenomena, such as fluids moving, such as data from computational fluid dynamics, where we are interested in understanding the different so the different intervals that define interesting events in a time-varying phenomenon. So these are just sample projects. Underlying all this, right, what truly drives us is the development of algorithms, the development of visualization techniques, particularly techniques that are driven by geometry. So we essentially develop these algorithms and techniques and apply them towards visualizing and analyzing data from these varied disciplines. So as you can see, this is a highly interdisciplinary field. We work closely we are experts in computer science, but we work closely with scientists from other disciplines like biology and like cosmology, in order to help solve some of the cutting edge problems in their domain as well. Right? In doing so, we also develop state-of-the-art techniques in computer science. So today's talk is going to focus on one of these techniques that we have been developing in our lab. These are techniques that are based on the study of topology. So my aim is to introduce this class of techniques to you. Of course, I will not be able to go into the details of all the techniques. Hopefully, this talk will motivate you to delve into this topic further and study it. There's a lot of resources available out there. So by the way, so now that I'm going to talk about the techniques, I'm happy to answer questions. So feel free to type them in. So for questions that you want to, for questions whose answer you want maybe immediately, you can maybe tag the question as now. And for those questions where maybe we can talk about it at the end of the talk, maybe you can just say Q&A and then pick a question. Right? I'm sure that the organizers will point any questions to me. Right. So let's start with a discussion of what data means in this context. Right. So I'm going to be talking about scientific data. Right. So scientific data is data that comes with a geometric context. Let's try to understand this with examples. On the left top, you see an image of a near infrared microscope of a tumor in a breast, right? So this is what is shown here is a tumor highlighted from a breast image. So what you see here is data from an electron microscope of a virus called the human adenovirus. So scientific data could refer to data that comes from such imaging devices. It could come from devices such as CT scanners, which image the human body in order to understand the bone structure and then maybe some tissue structure. The data could come from sensing devices like thermal scanners and pressure sensors and so on. The data could also come from simulations. So for example, here is data from an atomistic simulation, so atom level simulations of a sponge-like material, where the material scientist is interested in where are the pores or the air pockets in this material. Simulation also is the choice for cosmologists when they want to study this large-scale structure of the universe. So again, data that we are interested in is scientific in nature. And what I mean by scientific is that the data is measured over a spatial domain, right? So in all these cases, on all the pictures that you see here, the spatial domain is just R3, just Euclidean space, right? So by the way, all the pictures that you see here are results of visualizations that we have created during the past, except in a few situations where I have given due credit. Okay, so we would like to understand the different patterns in this data, right? Now, in order to understand these patterns, we have a variety of techniques at our hand. So what is visualization? So visualization is essentially the use of visual representations in order to understand patterns in our data. So we have been using visualizations since our early school days. We plot graphs, we look at charts, right? Scientific data has also been visualized since the past 40 years. So computer-based visualization techniques began with the development of something called isocontours or isosurfaces. This is something we see in the newspapers when we look at temperature or height values. So what you see here is a terrain map which is visualized using isocontours. So every curve here corresponds to a collection of points that have a given height. So this is a very interesting way to visualize this data, which is terrain elevation over a particular terrain. So this technique is very useful. However, it quickly becomes difficult to manage when you go, for example, to 3D, when you have, let's say, something like density measured over a volume. And you can extract, again, an isocontour. Here it becomes a surface, right? And the surface can easily be very complicated. And so it's difficult to make sense out of this surface. Even when the surface is interesting, right? And it's easy to interpret, there may still be difficulties. For example, what you see here is surfaces from the CT scan of the human foot. You see that individual surfaces do make sense. So these are individual surfaces, iso surfaces. So for example, this is a surface extracted at value 80, right? So these are the set of all points in the volume that has value 80. So this corresponds to the skin. At value 200, we have a surface which corresponds to the bone. However, it's difficult to identify these interesting iso values. And it's difficult to display all the iso value, all the iso surfaces, because you can imagine that this surface will occlude this surface if I display the two of them together. Right? So these are difficulties with the classic visualization techniques. Another classic visualization technique is volume rendering, where you display the entire volume using transparency. So here, transparency or slicing is used to understand what are the inner details of a particular scan again, right? So here you can see the bone structure, some of the blood vessel structure, and the skin structure. This again becomes very difficult to interpret when your data becomes large in size, when it becomes, when there are several features in the data. So for example, in this simulation of, again, the universe, while we can see individual clusters of galaxies, it becomes difficult to understand what is happening in these thread-like regions that connect different clusters of galaxies. Right? So this essentially leads us to a discussion on what are the challenges in understanding data, in visualizing data. Right? So there are two challenges that I want to talk about today. There are, of course, many challenges. One is due to the increasing sizes of data. Right? We all know, we all are aware of this. The presence of imaging devices with increasing precision, right, with increasing fidelity, and the availability of large computing resources that allow us to run simulations on larger data sets, right, results in large data sizes, and visualizing them becomes a difficulty. More important for us is that the data is becoming feature rich. We are able to run simulations which is able to identify features at different resolutions and with high fidelity. So we would like to visualize these data, and there are lots of features, and the human is able to look at only a select number of features within the screen. Right? So how do we design new techniques so that we can visualize feature-rich data? So this requires us to integrate data analysis. By data analysis, I mean classic data analysis techniques, modern data analysis techniques, including machine learning, deep learning, and so on, together with visualization, right? In order to help us understand patterns in our data. So traditional visualization techniques do not work. We need to abstract data in different forms. One way to abstract data is to use what is called topology. Right? So that is the topic of today. So let's try to understand this without going into technical details. What you see here is the CT scan of the human torso that we saw a few slides ago. using a topological structure like this is a tree that we will see later today. We are able to generate a visualization such as this, the middle figure, where the bone structure and some of the organs are highlighted in the visualization. So this is the benefit of using an topological abstraction such as this tree to enhance the visualization. So similarly, even in the study of cosmology, we are able to extract certain structures and use them to highlight interesting features in our data. Right? So I introduced the term topology. So now we may want to understand that. Right? But before doing that, let's quickly look at another class of data, which is equally interesting, and which is something that many of you may have worked with. So this is high dimensional data, data that comes in tabular form, data that comes from spreadsheets and so on. Right? I would like to think of this data as just a point cloud, just a set of points in some high dimensional space. Right? This is easy to imagine because any high dimensional data is essentially a vector, and you can think of this vector as a point in a suitably high dimensional space. And once you talk about point clouds, we can employ various dimension reduction techniques to reduce the dimension of this space so that we can display the data and understand features and patterns in the data. So what do we mean by patterns in this high dimensional data? Something that would be common is to look for connected components or clusters. Right? So again, many of you may be familiar with this. If you have dealt with high dimensional data, you try to do clustering. Now here what you see is very clear clusters. There are 3 different clusters. So this is one way to talk about the shape of your data, right? Or connectivity of your data. But what if I introduce a little bit of noise, right? So this is essentially the same data set with a few points that are noise. Now the clusters or the components are not so clearly identifiable, right? So do we still say that there are 3 components? Do we say that there is only 1 component? What is the shape of this point set, right? Has it changed suddenly because you have introduced a few points? So these are interesting questions. Now the questions do not stop here, right? There are other ways in which shape manifests itself. For example, the set of points could form loops, right? So how do you identify such shape of data? The kind of clustering techniques that you may use for identifying clusters may or may not work here. Again, when you have noise, do you see the loop, or does the loop suddenly get filled? Right? So noise again tries to make the problem more difficult for us. There are again yet other types of shapes. For example, forking behavior, right? So here what you see is a fork in the data, right? So this is a single component, but it is a little bit more interesting than a single component in the sense that there is a set of points here that seem to distinguish between the 3 arms of our data. Right? So how do we identify such shape of data and use that to understand interesting patterns that may lie within our data? So, so we have talked about shape so far in a very intuitive manner, right? We would like to, of course, formalize this, right? And before formalizing, we have to talk about what is shape. So we have been talking about points here, right? And in our mind, we have filled these set of points with a circle, right? Or an annulus. And so we talk about a space in this 2D plane, and we talk about the shape of that annulus or the circle. However, when we are talking about a computer-based representation of shape, a set of points is just a set of points. It does not represent a continuous space. Right? So we have to somehow go into a continuous space. One way of doing that is by just thinking about the points as weighted points, and each point can be considered as a point with a ball or a disk centered at that point. Now the union of all these disks will give us a particular continuous shape, right? And that is what we would like to characterize. Okay, so with that, let's talk about what is shape and how do we want to characterize it, right? So, this takes us to the discussion on topology, right? So what is topology? You may have heard this term in different contexts. If you are a computer scientist, you've probably heard this in the study of graphs or in the study of computer networks. If you are a mathematician, then you have probably taken a subject on topology. Topology is essentially the study of how space is connected. We do not care so much about geometry. We care only about how spaces are connected. So let's use an example to understand this better. There's a classic saying that goes, topology is the study of a branch of mathematics where you cannot distinguish between a coffee cup and a donut. So for a topologist, these two are essentially the same because you can deform one into the other without pinching, without gluing, right? So as you can see in this illustration. So essentially for us, we do not distinguish between the different geometries that you see here. For us, these two shapes are essentially the same. Right? So this abstraction allows us to do various analysis much more efficiently, as we will see. So topology is a very old branch of mathematics. The origins go back all the way to the 18th century, essentially to graph theory, right? So which goes back to the resolution of the Königsberg bridge problem by Euler. Hopefully you have heard of this. Right? So I won't talk about the Königsberg bridge problem, but suffice to say that this bridge problem was essentially solved by abstracting away the geometry of the bridges and representing them just as a graph, which stores how the different bridges are connected, essentially. Right? So similarly in topology, we don't care about what is the size of a sphere, what is the size of a disk, what is the size of a ball. We care about how it is connected. Now, how do we talk about different shapes? We talk about them using invariants. So one invariant is the Euler characteristic. So you may have seen the Euler characteristic in graphs. This is called the Euler number. So in the case of graph, for example, for planar graphs, the Euler characteristic is essentially the number of vertices minus the number of edges plus the number of faces. You may have seen this in your graph theory introduction. So this is a very simple invariant for a space. Another invariant is connected components. How many components do you have? How many connected components do you have? So these are interesting invariants for one-dimensional spaces like graphs. When you go to higher dimensional spaces, you talk about other invariants. For example, how many holes do you have? How many tunnels do you have in the space? For example, in this particular space, let's assume that this is a donut, as in it's a filled donut that you can actually eat. The number of holes is actually only one, right? So that's the one around the handle, or which is the central hole that you see once you see the donut, right? So both have a single hole or a single tunnel. Another invariant is voids. How many empty volume spaces do you have, right, in the space? So again, in the case of the donut, there is the number of voids is 0, right? If you have just the shell of this donut, then maybe then you can say that the void component is 1. There is a single void. So these invariants can be represented using group theory, and there is something called homology groups. So I'm just introducing these terms here so that you can look them up for future reference. Right. So topology is a very interesting branch of mathematics, and computer scientists have jumped in only recently to look at algorithmic questions in topology. So that is where the topic of today comes in, topological data analysis. Right? So topological data analysis is essentially the study of algorithms in order to construct the topology of space, in order to store them, in order to measure, and to query and compare these topologies. Specifically with the aim of data analytics, right? So that is what TDA really stands for. And this is a highly interdisciplinary field. This is even younger than visualization, only about 10 years young. Some of the researchers who are looking at topological data analysis come from a typical computer science background with interests in algorithms, fast computation, visualization, computer vision, and so on. There are several statisticians and mathematicians who are interested, for example, in machine learning, manifold learning, etc., and topologists who are interested in different aspects of topology, who are working together to develop these new techniques for data analysis. The applications of TDA is really wide. It goes all the way from material science, sensor networks, very engineering-oriented topics, to science-oriented topics like neuroscience, biomedicine, to applications to business analytics, even sports analytics, right? So you will find a lot of resources on TDA, including lectures, videos, tutorials, and so on, available. And some are also available from our webpage. So what I'm going to do in the rest of the talk is to discuss two specific topological structures, so you can get an in-depth view of what they are, how they are constructed, and then we will look at some applications. I'm just pausing to make sure that there are no questions. Okay, I don't see any, so maybe we will continue with this. So the first topological structure that I would like to introduce is called the Morse-Mail complex. I would like to introduce these structures using pictures, right? That's what we can do within 5 minutes for each topological structure, right? So let's imagine that we have an input data and we are representing it as a real valued function, right? So this is our input. This is a real valued function. The function values are mapped to color, low to high, right? And so low is red and high is yellow or golden. So you can see that the function is very simple here. There are two maxima, right? And they are already represented here using the red dots. The function has multiple minima, which are represented using the blue dots. And in addition, the function also has another type of criticality. These are the green saddle points. In the terminology of terrains, these are also called passes, right? So these are the three kinds of points where the gradient of the function becomes 0, right? Or the tangent plane is, in this case, parallel to the ground. So let's look at gradient lines here. Right? So this is, for example, a gradient line. So what is a gradient line? These are maximal lines that trace steepest descent. So you imagine that you are on this line anywhere. You follow the steep descent as you go down, right? So as you keep going down, you're following the steepest descent. You will essentially terminate at one of the local minima. Right? And if you keep going up, increasing gradient, you will terminate at a maximum. So you can imagine drawing such lines in the entire domain, right? So the origin and destination of these gradient lines have to be critical points, right? Because these are essentially the points where the gradient is 0. The Morse-Mail complex, that is what we are concerned about, is a partition of this entire domain, right, into regions that have similar gradient lines, right? So that have gradient lines that share the same source and sink. So what you see here are a few examples of cells in the Morse-Mail complex. So I'll just try to describe this again using the picture. So what you see in yellow here is a set of gradient lines which share the same source and sink. For example, the maximum on the left and the minimum on the top middle, right? Similarly, the cyan set of gradient lines share the same maximum and a common minimum as their source and sink. So you can quickly see that that the Morse-Mail complex essentially is a partition, and it has cells of different dimensions. So here I plot or show these cells. So these 2D cells are all quads that you can see, right? The nodes of these quads essentially is a maximum, a green saddle, followed by a blue minimum and another green saddle. So these are the two-dimensional cells of the Morse-Mail complex. And of course, their boundaries are one-dimensional cells that again connect critical points, right? So this graph-like representation of the partition is called the combinatorial structure of the Morse-Mail complex. So this is a topological structure. Once you look at just this graph-like structure, you can see that you have abstracted away, you have removed all the geometry. You care only about which critical point is connected to which critical point. It doesn't matter how far it is, right? Or how different it is in terms of function value. You just care about who is connected to whom. This is a very simple representation, but in practice, this turns out to be very powerful. So here is a quick application of the Morse-Mail complex. I'm playing a video.
In this video, we demonstrate our topology-based visual exploration framework for cosmic filaments. Cosmic filaments are gigantic tentacle-like structures comprising of millions of galaxies. They serve as a mass transport mechanism between dense collections of galaxies known as clusters. Regions of space where the density of galaxies is much lower is referred to as cosmic voids. Filaments exist in cluster-like regions and void-like regions. They also connect cluster-like regions across void-like regions. We propose the use of a density range-based query method to interactively explore different kinds of interesting cosmic filaments. The query is efficiently translated to extract relevant filaments from a topological data structure called the hierarchical Morse-Mail complex. Here, the query was adjusted for filaments within high-density cluster-like regions. The extracted filaments are visualized by the orange linear elements. Filaments within voids form interesting objects of study which are not easily extracted using earlier method. Here, we extract filaments within void-like regions. The queries demonstrated in this video execute in real time. Thank you for your attention.
Right. So that was just a quick video describing how the Morse-Mail complex and the combinatorial structure of the Morse-Mail complex was used to look at these filaments in the universe. So what we talked about in the previous slide, the arcs are essentially shown here in red. Of course, there is a lot more to this than what I described. If you want further details, you are more than welcome to look at our lab's webpage. The name of this project is FELIX, F-E-L-I-X, and it studies the cosmic web. Okay, let's move on to discuss another topological structure called the contour tree. So again, we look at a scalar function. So that is defined as this. It's defined over a domain D, and it takes real values. The contour tree studies the topology of these so-called level sets, right? So these isocontours that we saw at the beginning of today's talk. So here in this picture, you see a very simple two-dimensional domain, just a part of the plane. And you see a scalar function that is mapped to gray values. So the low values are dark and the high values are brighter, right? More towards white. So you can see that there are two minima here denoted as B and C. And there is a third one denoted as A. These are local minima of this scalar function f. What you can also see in the blue curves are different level sets. So each curve, if you try to trace it, is a set of all points that have a given function value. Right? So naturally it is continuous, right? And it terminates either on the boundary of the domain or it forms a closed loop. Right? So the small ones are next to the minima, and as you go away from the minima, the size of these level sets increase, and at some point of time they merge together into a figure of 8, and then they keep increasing in size. So you can see that these level sets change their connectivity. They go from one component to two components and then merge and so on. This evolution is stored in the form of a tree. This tree is called the contour tree. So in order to understand this, let's look at an animation, right? And see how this tree kind of evolves. Right? So here you see a similar function, but essentially the same function with just a minor difference, but it's shown as a surface. And you can see the evolution of the level sets as you increase the function value. Right? So you see that the boundary of this black region is the level set. It has two components now, right? And as you go away from the boundary, you will see that it will now have a single component, right? And as you hit the green point, it splits into two components. And as you go towards the maxima, one of the components vanishes, one on the left, and then finally the component on the right also vanishes. Okay. So this video will play again. So you can see that as you begin, there was one component that merged into another component and so on. So this change in topology is what we want to track. And you see the tree overlaid on top of the domain. This is shown using these nodes that correspond to the critical points and the arcs that connect these critical points. So again, we look at critical points, but the connections now are in terms of how the level set behaves or how the isocontour behaves between these critical points. So these arcs between the critical points form pairs, and these are called birth-death pairs that corresponds to the creation of a isocontour component and the death of this component. And this pair represents interesting features in the data. For example, they represent valleys or mountains in this terrain. And you can measure the size of these features using a notion of something called topological persistence. This represents how long this feature was alive during this sweeping process. Right? So again, these terms can be defined more formally, and I will point you to some references from our lab's webpage where you can look at further details. So the contour tree is the subject of interest, is the topic of interest for us. And it has several applications similar to the Morse-Mel complex. So now let's talk about a few applications to end the talk. The first set of applications is in the study of symmetry in scalar fields. So here, what you see on the right is a visualization of heat distribution in a conductor. So this is a metal conductor, and we are looking at heat or temperature distributed within this conductor. You can see that the left leg and the right leg are symmetric copies of each other with respect to their geometry, but they are also copies of each other with respect to how the temperature is distributed within them. We would like to capture this somehow automatically. All right. So in general, we would like to capture repeating patterns in our scalar field. So given a scalar function, again here f is just the temperature distributed over this domain. We would like to find out if m1 and m2 are symmetric with respect to each other. So we want to find if there is a transformation t that will take m1 to m2. In this case, the transformation is very simple, right? It's just a translation. And I would like to see if this translation will also preserve the function values at those points. So f at x, so if you take a point x in m1 and look at the temperature at that point, I would like the temperature to be equal to the temperature at t of x, right? So I want the temperature values to also be preserved by this transformation. Now this is a very difficult problem because I don't know I don't know what are all the symmetric regions. All I have is m. I don't have m1 and m2. Further, I don't know what t is. What are the different transformations that I should be looking at? Right? So this is a challenge, and it has been studied in different domains within computer graphics, computer vision, and in data visualization. So our solution was via the use of topology. And why are we interested in symmetry at all? Because symmetry appears in nature in many ways. For example, in virus structures, we see symmetry all the time. So here is a particular virus called the human adenovirus that displays 20-fold symmetry. Here is a protein which displays rotational symmetry. So symmetry is present in various biomolecules. It is present even in the study of fluids. So you see symmetry in flows and so on. In many cases, the lack of symmetry, the missing symmetries are also an interesting indicator of what is happening. So there is a clear reason for us to study symmetry. So what we developed was a way to visualize data that highlighted symmetry. So what you see on the top row is visualization using classic techniques. So you see the human adenovirus, and then a few a few protein molecules in the next columns. We can ignore the second row for now. The third row is the visualization of these same data sets. But now what we do is to highlight the symmetry in the data. So, so here we see the zoomed in version of the human adenovirus. You can see that the original visualization is good for the human eye. We see actually with our eye that there are these tentacle-like regions which seem to be copies of each other, right? But it's very difficult to identify that they are all actual symmetric copies. So this is an automatically generated visualization that identifies the symmetric regions and highlights them in this display. Right? So there is actually 20-fold symmetry. If you rotate this around, you actually see that there are 20 such tentacle-like regions. And the difficulty here is that there is a lot of noise in the data, and still our method is able to identify these symmetries. Okay? So the symmetries can be of different kinds. So here, for example, the first column we identified dodecahedral symmetry. The second column we identify rotational symmetry. And in this column, we identify a very interesting symmetry called corkscrew symmetry, kind of a twisting motion. And then here, this is simple translational symmetry. This is symmetry at different resolutions. There is one symmetry for the outer lobe, and then there is one for the inner part of the molecule. Symmetry, like I said, appears in the study of fluids also. So we are able to identify symmetry in vortex flows and in the study of fuel in a combustion chamber. You can also use symmetry to identify if there is any error in your simulation. So for example, here, what we identified was some additional symmetry that was not expected. The researchers that we worked with went back to look at their simulation code and identified that there was actually a missing boundary condition, a missing corner case, and they were able to fix that quickly. Right? So visualization also functions as a very simple but sophisticated debugging tool. Right. So some of these symmetries have also been applied to specific application domains. So we have released a web server that can look at symmetries in what is called electron microscopy data. Right? So EMDB stands for electron microscopy database. And we have a server that allows a biochemist or a biologist to look at symmetries in electron microscopy data. Again, feel free to look at this online. We extend this notion of symmetry to the study of similar structures over time. So let's look at this video, which is flow behind a cylinder. So the particles are flowing, or actually fluid is flowing left to right, and there is an obstacle here in the middle, which is like a cylinder. So this is a very classical study where one can see vortices being shed in the wake of this cylinder. So the vortices start forming after some time. You will see them forming now. And what is interesting is that they start forming along a street. This is called the von Karman vortex street. Right? So they are actually forming now. You can see that there are two types of vortices, the one with the positive spin clockwise and the one with the negative, the counterclockwise spin. Right? So these are actually turbulent structures. They are studied very much within this computational fluid dynamics field. What we were able to do is to analyze this data and identify that the periodicity in these vortices. So these vortices were actually shed at regular intervals. And with a study of just the topology, we were able to identify this periodicity. So the plot actually shows the similarity in the vortices between the first time step and the tth time step. So t goes from 0 to 900 here. And so we see a lot of similarity at these time intervals. T equal to 0 is similar to t equal to 75. That denotes a 75 time period. We also notice a half time period of 38 where there is a flip in symmetry. So this study using topology can help even in time varying data analysis. So cyclones are again vary over time, something that we often experience. But in this study, we are looking at extratropical cyclones. These are cyclones for example, over Australia, as you see here, or over the European continent. So cyclones appear far more frequently in these regions, and they are less intense. They bring a lot of rainfall. An important problem is to be able to track these cyclones over time. This is a difficult problem because cyclones are not as prominent as the kinds we see in the tropical region. So for example, in this video, what you see is a visualization of the cyclone over, I think it just ended. Let's see this again. Right. So you see the path of the cyclone shown here, and you will see that the cyclone genesis right now, and you will see that the cyclone actually is a collection of multiple depressions. So here till now there's just a single depression, but you will see later that there are multiple depressions that together form the same cyclone. It is very difficult to identify that these depressions together form a single cyclone. What we were able to do is to use topology-based techniques to identify the presence of a single cyclone and to track it over time. So this was another application. So the final application is to data summarization. So similar to the flow behind the cylinder, we can think about a flow behind a cylinder in 3D. So this is what you see in the pictures here. And here what happens is a phenomenon which is very similar. You see a vortex street, a set of vortices that form behind the cylinder. Now we would like to identify interesting time intervals for various parts of this time varying phenomena. So what we did was to study the similarity between the various time steps in this time varying data, right? So we had time, for example, go from 1 to 98, and we had at every time step a snapshot of the data. So in this case, this was the vorticity of the data over the entire volume. So this is just a simple vector that describes how the fluid is moving. So we compare this for the 0th time step with all other time steps. That's the first row. And the second row compares the first time step with all the other time steps. So this is essentially a similarity matrix or a comparison matrix. And we study this comparison matrix to understand that there is a first phase in this simulation where really nothing much happens. Almost every time step is similar to the other. So this is where the vortices are yet to form. There is a second phase which is distinct from other phases. This is where, this is shown with the green box. This is where the vortices begin to form. And then there is a third larger green box, where you see a lot of repeats, a lot of symmetry in the patterns you see here in the similarity. This is where the vortices are being shed at regular intervals. So this is at nice intervals. And then later, towards the end, the vortices die away, right? And the flow becomes highly turbulent. This is the fourth part of your simulation. So with, again, a topology-based analysis, we are able to summarize our entire time-varying data into these 4 intervals. So this is a very useful step in analysis of time series or time-varying data. So with that, I would like to summarize, kind of come to an end of this talk. So I talked about some challenges in data analysis and visualization, particularly with the data becoming feature-rich. And I proposed the use of topology-based representations such as the contour tree and the Morse-Mail complex. So these representations lead to a new class of visualization called feature-directed visualization. What I did not talk about is algorithms for computing these representations and algorithms for actually displaying these representations. But I would like to note that these algorithms happen to be combinatorial algorithms. So they are like, they essentially include a combination of graph search, vertex, simple sorting, searching algorithms. They do not involve any numerical computation. So this leads to very fast and efficient implementations. Often these implementations are also parallel in nature. They run both on the GPU and on multi-core CPUs. All the code that we develop is made available on our webpage. You are welcome to download and try them. We also have videos describing these results on our YouTube channel. Feel free to have a look at this. So I'd like to stop with that. Of course, I don't want to stop without acknowledging the massive amount of work done by the students in the lab. So what you see in the bottom picture here is our current group. a very talented and motivated set of PhD students, project staff, postdocs, and some interns who are now gone. On the top picture, you see some of a group from a few years ago. Many of these students, alumni, are actually research scientists at top universities all over the world. They are, one is actually started a company, the others are holding big positions in looking for talented, motivated students at all levels. Once in a while, I do have openings for project assistants. And if yes, I will advertise this on my webpage. Feel free to look at it. So these positions are often also longer term, 1 to 2 years. We also have positions in a startup. So this was a startup founded by my student, Nitin Shivshankar, together with a mechanical PhD from IISc. This is a startup that is right now housed in IISc. It's called Mimic, and they focus on developing simulators for endoscopy. They have already a product out. They are looking for people who have an interest in gaming, computer graphics, design of CAD models, and so on. Some of these positions are joined with our lab, VGL, the Visualization Graphics Lab. So with that, I will end my talk, and I'm happy to answer questions. I did notice that there are a few hands up, but I didn't see the questions, so I couldn't respond to that. But I'm happy to answer questions now.
Hello, sir.
Yes.
The first question is it possible to apply topological data analysis to text analysis or natural language processing? And also, is word embedding can be considered as an example of topological data analysis?
Okay, so that's a very important and relevant question. The answer is, in principle, yes. I may not be able to give you an exact reference, but topological data analysis has been used extensively for various high-dimensional data analysis classification tasks. So I'm sure that this includes text analytics. For example, one reference is this company called IISd, AYASDI. So IISd is essentially, they brand themselves now as a machine learning company, but they were some of the pioneers in TDA, and they use topological data analysis for various tasks. And among them, I'm sure text analytics also plays a role. So the way TDA helps with, for example, something like text analytics is once you have an embedding of your words or documents in the form of a vector, right? TDA helps you understand the shape of this data in a very intuitive manner. So you can understand very easily the different patterns that are present, and then apply suitable classification techniques and so on. Right? So that is how it helps.
So the next question is, are there any specific programming tools used for topological data analysis?
Okay, that's also very interesting, important question. So like I said, IISd is a company. Of course, their software is commercial, right? So I don't think they have an academic license. They used to have one. So some free tools that are available. One is TDA. It's called TDA in R. So if you're familiar with R, there is a TDA package in R. This is probably the most comprehensive of the different tools that I know. You may also want to look at a tool called TTK, Topology Toolkit. This is a very interesting tool that combines TDA techniques together with visualization. That's a second tool. A third tool is called Goody. This comes from INRIA in France. A fourth tool is for Morse-Mail complex and for contour trees from our lab. So you can look at our lab's webpage to download these tools. So maybe I'll stop there.
Sir, what role does machine learning play in topological data analysis is the next question, sir.
Right. Okay. So this is a very interesting, there's a very interesting interplay between machine learning, statistical learning, and TDA, right? So there are two ways in which the two areas come together. One is the more traditional approach. So we talked about various topological invariants, right? Function as priors for your favorite classification technique, right? So you could use, for example, the number of loops, the number of components. These can be computed very efficiently and robustly, and they can serve as priors or additions to your feature vector. So this has been used successfully in many applications. That's one way in which this comes together. The second is to actually improve your TDA techniques using machine learning. So, so for example, how do I, so I compute some structures like the contour tree and the Morse-Mail complex, right? So some of these computations result in a very large graph, in a very large tree, right? So how do I look at interesting regions within this graph? So again, you can use machine learning techniques together with TDA to solve the problem. So some of the more recent advances are in the use of TDA to improve deep networks. So this is still at the very foundational stage. So people are still trying to define what it means to talk about gradient descent for TDA. Right? So I think there are some initial answers, but I don't think we have tools yet that use deep learning together with TDA. But for all the other classic machine learning techniques, there are already tools available that combine the two. So for example, I think with scikit-learn, there is also some TDA tools available. One is called Mapper that you may want to look at.
So the next question is, what are some of the open problems in topological data analysis related to healthcare domain?
Okay, right. So let's see. In terms of techniques, right, TDA is still very, very young. So we are still looking at some of the so we are still looking at data from a unidimensional viewpoint. So all the examples that I gave you today were for scalar functions. These were for just real valued functions, right? So when you talk about the healthcare or medical domain, often the data comes in multiple columns. There are multiple features of interest, right? So the analysis techniques should also be able to extend themselves or generalize themselves to multivariate data, right? So this is a challenge in TDA. How do I apply TDA techniques for multivariate data, right? Where I'm interested not just in temperature of the person, I'm interested in temperature, their blood glucose levels, together with symptoms, right? How do I use all these to decide what kind of disease they have, if it's prediction, or if I'm looking at, for example, a population, and I want to understand if there are different classes of people, right? So who is diabetic, who is not diabetic, right? And I don't often have a single parameter that decides who's diabetic, who's not. I will often have multiple measurements. So we would like to extend TDA to multivariate data in order to do this kind of healthcare studies. So that is a key challenge, I think.
Mr. Veena?
Sir.
Mr. Veena?
Yes, sir.
Can I talk to Dr. Vijay Natarajan?
Yes, sir. Sure, sir. Please go ahead, sir.
Sir, this is Siddharaj once again, sir.
Yes, please. Yeah.
Sir, can it possible to consider our PG and UG students for your research activities or internship activities in your place, sir?
Okay, yeah, so that's why I ended with that slide, right? So I think I mentioned to a few of you, I've had one very very good experience with a student from Dr. AIT, someone who graduated a couple of years ago with a bachelor's and then joined our group as a project assistant, worked for more than a year, almost 1.5 years, I think. He worked in our group together with Mimic, and is now pursuing a master's. So this, I'm always looking for motivated students in this form, right? But you will, I'm sure all of you, the students and the faculty will agree that there is a lot of background required in order to get started and do something useful here. So I always look for candidates who can spend at least a year, maybe 2 years in the lab in order to do something productive. Internships are good. We have a department-wide internship, and I will encourage students to apply through that. And I do take interns through that route.
Sir, actually, some of our students pursuing their internship in aerospace engineering division at IISc.
Okay.
I want to play.
I'm sorry, I'm
happy to share our talented students in your IISc activities, sir.
Okay, I think after you said aerospace, I missed some of the sentences that you spoke.
Thank you, sir.
Yeah, can you say that again? I missed the question.
Sir, so some of our students actually already is pursuing their internship in aerospace engineering division at IISc.
Okay, very good. Yeah, yeah.
And now I want to place some students to under your supervisions to pursue or to carry out that internship in this TDA.
Okay, so like I said, yeah, I think this would be good. It's all case by case basis, right? If we have projects where we can give something useful to the students so that they can do something in 2 months, then great. Right, so we have this department-wide internship. We call for it, students. I'm happy to look at applicants at that time, right? But in order to, right.
Thank you, sir. Over to Veena.
So one more last question, sir.
Yeah.
Can we use topological data analysis for regression problems?
Yes, so I think that has been tried. I'm sure. So just like the other machine learning techniques that I mentioned, right? So if you want to do classification, you can always use TDA to improve your classification results. So similarly for regression, you may be able to improve your regression results by looking for certain topological techniques. For example, something that people have tried to look at periodicity in data, right? Periodicity doesn't show up easily in when you just plot the data directly. However, if you transform the data to an appropriate space, right, periodicity shows up as nice loops, and then you can use regression together with TDA to identify the periodicity in your data. So in some cases, yes, the two can be combined.
Okay, dear participants, any more questions, please?
I hope this is the time to conclude, Gowrishankar and Veena.
Yeah, sure, sir.
Yes, sir.
Because sir is waiting for the other activities. Eh?
Oh, sure, sir. So there is an end to everything, but we believe there is never an end, but always a beginning. Hence, we conclude today's webinar with vote of thanks. First of all, I would like to thank our speaker, Dr. Vijay Natarajan, sir, for making this webinar very informative and interesting. I like to thank Dr. Siddharaju, sir, Dean Academics and Professor and Head of the Department of Computer Science and Engineering for his continuous support and encouragement. I also wish to express my gratitude to our principal, Dr. C. Nanjundaswamy, sir, for providing encouragement and support in his absence. I would like to thank all the coordinators for organizing and making this webinar a success. I thank all the participants and we appreciate you being here. Thanks once again for joining us today. And thank you all for your cordial cooperation. Thank you. Over to you, sir.
Thank you, Professor Natarajan.
Thank you, ma'am.
Thank you for your wonderful time.
Okay, thank you very much.
We are looking
Thank you,
forward
Dr.
to
Vijay, sir.
the future also. Thank you, sir.
Thank you.
Yeah, thank you, sir.